Hi everyone! Welcome to part 3 of chapter 6. Earlier in the chapter, we learned how to draw Lewis structures, and last time we learned how to use those Lewis structures to help us determine the shape of a molecule. Today, we are going to use the Lewis structures to help us determine the attractive forces that are present in the molecules and between two molecules of a substance. Later, we're going to use these attractive forces to help us think about the properties of different types of molecules. So let's go ahead and get going. So first, we're going to start off by reviewing our states of matter, just kind of briefly. So our first state of matter that we're going to talk about is gases. So gases contain particles that are really, really far apart. These gas particles are moving in random motion. So as you can see, these ones are going in kind of all different directions here. And they are doing, they're completely independent of one another. So it doesn't matter what each gas particle is doing, they're all acting independently. So they're just kind of zooming around, doing their own thing, and very, very far apart. So there is little to no contact between these gas particles. They're all, like I said, acting kind of independently. And there are no attractive forces between the molecules. Essentially, what has happened is these molecules have so much energy that they were able to overcome the attractive forces that are holding them together, and they just kind of zoom away. So this is in direct contrast to solids. Solids contain particles that are really close together. So this is essentially exactly opposite of gases. They are very, very, very close together, and they have a very rigid shape, like the chair you're sitting in or the pencil that you're holding, right? They have a definitive shape, as opposed to gases. They don't actually have a shape. They just take the shape of whatever container they happen to be in at the time. But solids have a definitive shape. They have really strong attractive forces that are holding those atoms and molecules in place, which is why they can't move around. Okay, so they're in very, very close contact with very strong attractive forces, which give it a rigid shape. Liquids are kind of in between. They're, have more attractive forces than the gases do, but fewer attractive forces than the solids do. So these liquid particles are still close together, right? They do have a set volume, just like our solids have a set volume, but they're different because they can take the shape of whatever container you put them in, right? They can flow. So liquids can take the shape of, say, a beaker or an Erlenmeyer flask or a graduated cylinder, or you can even kind of spill it all over the ground, right? But the reason that they can take the shape of different containers is because their attractive forces are not as strong as a solid. So they're able to kind of slide past each other. So they're in close contact just like a solid is, but they have weaker attractive forces than solids do. So we're going to say they have some attractive forces, which gives them a fluid kind of shape. So what are these attractive forces that I keep talking about? We have two different types of forces, and we've actually already learned about one of them. We just didn't really call it an attractive force. So what we've learned about so far, these are called intramolecular forces, otherwise known as bonding forces. These are the forces that exist within a molecule, and they are going to influence the chemical properties of our substance. So intramolecular forces are going to be things like ionic bonding, covalent bonding, right? Those are going to be intramolecular forces. These are different than the ones that we are going to focus on this time. So this is going to be the focus of today's lecture. Again, we've already learned about bonding forces. We just didn't talk about it this way. So we're learning about intermolecular forces or non-bonding forces. These are forces that exist between two molecules. So like if this was a molecule and this was a molecule, they would be the attractive forces between two molecules. Okay, that's inter as opposed to intramolecular forces, which are bonding forces. Like I said, this would be something like an ionic bond or a covalent bond. Okay, but intermolecular forces exist between two molecules, and they are going to influence the physical properties of a substance. Remember, we've already learned about chemical and physical properties. If you're, kind of rusty on them, you might want to brush up just to remind yourself of what they are. But chemical properties are going to be things like how our substance reacts, whereas physical properties are going to be more like the shape or the density or the color. Okay? All right, so let's focus on these attractive forces. And we're going to, again, look at the ones between molecules. So these are intermolecular forces. That's going to be the focus of today's lecture. Okay, so these intermolecular forces hold liquids close together, hold the solids close together, right? They're those forces that are existing between two atoms or two molecules to kind of keep them close. Okay, solids melt and liquids boil when the attractive forces between the molecules are broken. So essentially what that means is when our substance is a solid, right? Those are going to be very, very, very strong attractive forces. But if I input some heat, then I give those atoms and molecules some energy. And when I give them energy, they're able to kind of overcome those attractive forces, and we'll see them go through a phase change. We can see the solid melt. That's the weakening of the attractive forces between the atoms and molecules. It's the same thing when we boil a liquid into a gas. That actually takes a lot of energy because we are going to completely overcome the attractive forces. The attractive forces in a liquid have to completely break, essentially, in order for that liquid to go into the gas phase. But we're going to talk more about this in a later chapter. Okay, so we're today going to look at what types of attractive forces there are. So there are 3 different types of attractive forces we're going to focus on in this class. They are dipole-dipole interactions, hydrogen bonding, and dispersion forces. Okay, those are the 3 that we are going to learn about. There are actually more intermolecular forces, but these are the main 3. All right, so let's kind of look at the relative magnitude of our forces. So at the top is ionic bonds. Remember, these are intramolecular forces. These are ones within a substance. Okay, so that's going to be an ionic bond. That's our strongest bond. And covalent bonds are also strong because, again, these are both intramolecular forces. And they are going to be very strong. Out of the intermolecular forces, we have hydrogen bonding is going to be the strongest, and then dipole-dipole interactions, and then London dispersion forces. So again, all these ones up here, these are intramolecular forces, and these are intermolecular forces. So bonding forces, the ones on the top, right, these are going to be bonding forces. These are stronger than our non-bonding forces, okay? Alrighty, let's go ahead and talk about each type of intermolecular force. So the first one we're going to talk about is hydrogen bonding. And this is kind of a bad name for this type of attraction. Okay, this is an attraction. It is not a bond. I recognize it says hydrogen bonding, but I want you to know it is not a bond. It's just a really bad name for this type of interaction. But it's a very, very strong attraction, so we call it hydrogen bond because it's almost as strong as a bond. It's not though, but it's a really, really strong interaction, but it's not a bond. So the way that we recognize hydrogen bonding is it's going to be between hydrogen and some other atom that's really electronegative. Okay, so our electronegative atoms that we're going to look at are oxygen, nitrogen, and fluorine. Okay, so I like to say hydrogen bonds just want to have fun. Okay, fluorine, oxygen, nitrogen. I know it sounds silly, but if you remember that hydrogen bonds just want to have fun, then I think that will help you out. So here's how we'll recognize it. We're going to find a really electronegative atom, like nitrogen, right? Because nitrogen shows up in Fon, and it's going to be attracted to a hydrogen on a different molecule that is bonded to a different really electronegative atom. So I like to think of this as like a hydrogen sandwich. Okay, we have nitrogen is attracted to a hydrogen that's bonded to a really electronegative atom. Okay, I know that sounds a little bit confusing. We're going to go through some examples. You'll notice, though, that when you're looking at this, nitrogen has a partial negative because it's really, really electronegative. Just like oxygen here has a partial negative because it's really, really electronegative. That makes hydrogen really, really electropositive, which is why we have this strong interaction between them, okay? Negatives and positives attract, right? You've heard of opposites attract. That's what's happening here, is we have a nitrogen that's a really electronegative atom being attracted to this hydrogen that's really electropositive because it's attached to an electronegative atom. Let's see this again. All right, here's some more. So here we have a nitrogen, which again is a really electronegative atom, and this one is bonded to the hydrogen, okay? And so that hydrogen is attracted to another, a really electronegative atom. So again, I like to think of this as a hydrogen sandwich. The hydrogen is going to be bonded to one really electronegative atom and attracted to another one, okay? So we're going to see this in polar molecules that have hydrogen that's bonded to an electronegative atom and attracted to a different really electronegative atom, okay? So again, because this nitrogen has a partial negative and it's very electronegative, that means hydrogen becomes really electropositive and it can be attracted to another really electronegative atom. So this bond-ish thing, right, this hydrogen bond that forms between them is very, very strong. But again, I want you to remember that this is an attraction, not a bond, okay? We see the same thing in water. Water has an oxygen, which is very electronegative, and it has a hydrogen bonded to that oxygen. So that makes that hydrogen really electropositive, okay? And that hydrogen can be attracted to an oxygen of another molecule, making a very, very, very strong attraction known as a hydrogen bond. Okay, so here we have it again. This molecule is called methanol, okay, and this is also a polar molecule. You'll see that there is a partial negative on oxygen and a partial positive on hydrogen. So again, this hydrogen is bonded to an electronegative atom and also attracted to an electronegative atom. And this here, that is the hydrogen bond. Just for a point of interest, do you see that the carbon, all of these carbon-hydrogen bonds here, do you see that there's no partial positives or partial negatives? Remember that a carbon-hydrogen bond is nonpolar because carbon and hydrogen have very similar electronegativities. So that's why you don't see these partial negatives and partial positives, because those bonds are nonpolar and we don't write partial positives and partial negatives for nonpolar bonds. Okay? So we see the hydrogen bonding happening between the hydrogen that's bonded to the oxygen. This hydrogen and this hydrogen and this hydrogen cannot form hydrogen bonds. I'm going to say that again. This hydrogen, and this hydrogen cannot form hydrogen bonds. Even though they are hydrogen, do you see that they are not bonded to a really electronegative atom? Carbon is not very electronegative, right? It's similar to hydrogen. So since carbon is not very electronegative, these hydrogens do not become very electropositive. So they're not going to form a strong attraction with another atom. We only see that when we have this atom being really electronegative, making this one really electropositive, so it's going to have a very strong attraction to another partial negative atom. Okay? So these really, really strong interactions cause these substances to have really high melting points and high boiling points. The reason that they have high melting points and high boiling points is because they have strong attractions between the molecules. And that is going to hold those molecules in place. So it's going to be harder to make them melt. It's going to be harder to make them boil because those attractions are so strong between the molecules. They're kind of holding on really, really strong and locking them into place. So it's going to take more energy to melt them and more energy to boil them. So as you can see, substances that can form hydrogen bonds have unusually high melting and boiling points. So remember, hydrogen bonds just want to have fun. So out of these, only water has one of those atoms in it, right? All of them have hydrogen, but remember, hydrogen has to be bonded to a really electronegative atom. Since all of the other molecules that are shown here don't have fluorine, oxygen, or nitrogen in them, these ones cannot form hydrogen bonds. only water can form hydrogen bonds here. Okay, so water can form hydrogen bonds, which means it has a really high melting and boiling point compared to the other molecules. Okay, so I know 0 doesn't sound like a high melting point, but do you see all of the other ones are negative? So 0 is a lot higher than a negative number. And here, if we compare the boiling points, 100 is a lot bigger than those negative numbers. So again, the reason that water has an unusually high melting point and an unusually high boiling point is because it forms hydrogen bonds. And those hydrogen bonds are very, very strong attractions that keep those water molecules close together. And so it's going to take a lot of energy to melt the ice. It's going to take a lot of energy to boil the water. Okay, so again, all because of hydrogen bonds. So if we look at this molecule, right, this molecule has a lot of hydrogens. But remember, the hydrogen has to be attached to a really electronegative atom. It has to be attached to fluorine, oxygen, or nitrogen. So here, this hydrogen is bonded to nitrogen. So that means that this molecule can form hydrogen bonds because that hydrogen is attached to a really electronegative atom. If we look at this molecule, this one also has hydrogens, but this molecule cannot form hydrogen bonds because there are no hydrogens on the very electronegative atoms. Like if we look at this oxygen, there's no hydrogens bonded to it. And if we look at this oxygen, there's no hydrogens bonded to it. So all of our hydrogens are bonded to carbon, and carbon is not a very electronegative atom. Therefore, it doesn't make the hydrogens electropositive, so it can't form hydrogen bonds. So that hydrogen has to be attached to fluorine, oxygen, or nitrogen. All right, thinking about all of that, I want you to pause here and tell me which of these molecules do you expect to be able to do hydrogen bonding? So pause here and then come back when you're ready to see the answer. Alrighty, let's go over this. So for the first one, right, this one cannot form hydrogen bonds because those hydrogens are attached to carbon. And remember, carbon is not an electronegative atom, so we are not going to see hydrogen bonds there. For this one, we do have a hydrogen attached to an electronegative atom. We have that here, right? So that means that this molecule can undergo hydrogen bonding because this oxygen will become partial negative, this hydrogen will become partial positive, and it can go form a hydrogen bond with an oxygen atom. Okay? This molecule down here, doesn't even have hydrogens, so it definitely can't form hydrogen bonds. And then this one here does not have any hydrogens on the electronegative atoms. Okay, so again, it can't form hydrogen bonds either because there are no hydrogens on oxygen and no hydrogens on nitrogen. All right, so that takes care of hydrogen bonds. It's kind of a special type of interaction, and it can be a little bit tricky to see. I really recommend you get some practice on that. But our next type of interaction that's not quite as strong as hydrogen bonds, but still a fairly strong interaction, is dipole-dipole interactions. And we will see these in polar molecules. So in order to be able to tell whether something has dipole-dipole interactions or not, you need to be able to tell whether or not the molecule is polar. If you're not doing great with determining whether something is polar or not, really make sure to get some practice on it because we're going to use it in this lecture and in future ones when we start talking about the properties of substances that are related to these intermolecular forces. Okay, so you need to be able to determine whether or not a substance is polar. Okay, but if it is polar, then the polar molecules are attracted to each other by dipole-dipole attractions. And all that means is that the partial negative side of one molecule is going to be attracted to the partial positive side of the other. And I think that makes sense, right? Remember, opposites attract. So all it does is these molecules will kind of orient themselves so the partial negative side of one molecule is facing the partial positive side of another molecule, and that negative to positive interaction is going to form a strong attraction between the molecules. So when we were looking at hydrogen bonding, we talked about water. And we said water forms really strong hydrogen bonds because that hydrogen is attached to a really electronegative atom, that oxygen, and it's also being attracted to an oxygen of another molecule. Okay, so hydrogen bonding, though, is kind of a special type of dipole-dipole interactions. It's only going to happen in polar molecules, but it will only happen in certain polar molecules, right? Though they have to have an oxygen, a nitrogen, or a fluorine, and also a hydrogen. Whereas dipole-dipole attractions can happen in any polar molecule. So hydrogen bonding is kind of a special type of dipole-dipole interaction that's really, really strong. So here, when we're talking about water molecules also form dipole-dipole interactions, which is why we're showing them here. So this is hydrogen, and then oxygen, and then hydrogens, and our oxygen. Okay, so when these polar molecules are put together, they're going to orient themselves so that the partial negative side of one molecule is going to be attracted to the partial positive side of another molecule. So here, oxygen gets the partial negative because it's more electronegative, so that means hydrogen gets the partial positives. So same thing down here. So as you can see, these water molecules oriented themselves so that the partial negative of one is kind of facing the partial positive of the other, and they're going to be attracted that way. And that attraction is called dipole-dipole interactions because they're being formed between two dipoles. All right, our last type of interaction that we're going to look at today is called London dispersion forces, or sometimes we just call them dispersion forces, or sometimes just London forces. Okay, but these are going to be for molecules that don't have dipoles. So this is going to be for nonpolar molecules and noble gases. Okay, so again, these are molecules that don't have dipoles. And so these London dispersion forces, they arise from the uneven, instantaneous charge distributions due to electron movements in nonpolar molecules. And I know that sounds like a lot, so I'm going to try and explain it. Essentially what happens is at any one point in time, the electrons can kind of hang out on one side or another side of the molecule. Remember that electrons don't really zoom around in these specified paths. We talk about them in terms of electron clouds, and they can kind of be in different places in the molecule. Okay, I'm not going to get too much into that just because we're going to fall off this cliff of quantum mechanics. So I'm going to try and keep it kind of vague, but essentially the electrons in the molecule can kind of shift around. And if the electrons kind of shift to one side or the other, they can make one side kind of negative and the other side kind of positive, which is why we call this an instantaneous charge distribution. So it just happens because in one point in time, the electrons are kind of heavier on one side than the other. Okay? So this is called an instantaneous dipole. The fact that the electrons are more on one side than the other side makes one side partial negative and one side partial positive. But just for a second, and then it goes back to being nonpolar. And then it happens again, and then it goes back to being nonpolar. And then it might happen again and go back to being nonpolar, right? That's that instantaneous dipole, and it's because the electrons are constantly in motion, zooming around the molecule. So if they temporarily make a dipole, right? The electrons are more on one side than the other. They can do what's called inducing a dipole in a neighboring nonpolar molecule. So if in our molecule, our electrons happen to be more on one side than the other, and it makes that side electronegative and the other side electropositive, then it can kind of force a neighboring nonpolar molecule to sort of do the same thing. And I have a picture that shows this in just a minute, which I think will help clear it up a little bit. So when they make these kind of instantaneous dipoles and induced dipoles, they will get a small amount of attraction between our molecules or between our noble gases. And so that's why nonpolar molecules can exist as liquids and solids, because they do have small amounts of attractions between these molecules because of these London dispersion forces, these instantaneous dipoles. However, since these instantaneous dipoles don't hang around very long, these are very, very, very weak forces. So they just kind of happen and they're gone, and they happen and they're gone, and continually doing that over and over and over again. But because they're not permanent dipoles like our polar molecules, then these tend to be very weak forces. So here's kind of a picture, and I think this will help. So here's, we're going to say two nonpolar gases, or let's say these are noble gases. I don't know, maybe these are krypton, okay? Two atoms of krypton. And so if we look at atom A and atom B, they both have a nucleus in the middle, and then they have some electrons floating around in their electron cloud. Well, at any given point in time, because these electrons are kind of zooming all over the place, let's say at some point in time, more electrons hang out on one side of this atom than the other. And so in this point in time, because there's more electrons on the left-hand side, that entire side becomes partial negative, which makes the other side partial positive, because one side kind of seems like it gained electrons, and the other side kind of seemed like it lost electrons. So within this one atom, we're kind of getting a dipole, right? When that happens, these electrons, right, remember, electrons are negatively charged. And if they see this positive charge here, the electrons are going to move because negatives and positives attract. So the fact that this is partial positive right now is going to send these electrons in this atom closer to it, which makes that side of the atom partial negative and that side partial positive because it was next to this other instantaneous dipole. So this here, this is called an instantaneous dipole because it just kind of happened, just because the electrons happened to be zooming around and ended up more on one side than the other. So that just kind of happens. When that happens though, and it forces these electrons to move like that, that's called an induced dipole that happens on atom B. Okay, so that's what happened. So atom B happened to have a dipole because one happened on atom A. Hopefully that makes a little bit of sense. But that's essentially how London dispersion forces work. The electrons happen to be on one side of the atom, and so that side became partial negative and the other side became partial positive, and that made a neighboring atom make a dipole, and then since their partial negatives and partial positives kind of line up, now there's an attraction between these two atoms. Again, it's going to be a very weak attraction because these dipoles are just going to hang around for a second and then they're going to go away. And then it's going to happen again and they're going to go away. So these interactions are very, very weak, but they do happen. All right, so since we have these London dispersion forces happening in, noble gases and in nonpolar molecules, right? We need to be able to compare the strength of these London dispersion forces. So essentially what happens is our London dispersion forces become more and more important. So they become greater and greater and greater London dispersion forces as the size of the molecule increases. So essentially the way this plays out, in the noble gases, xenon would have the greatest London dispersion forces, and out of our diatomic halogens, iodine would have the greatest London dispersion forces. And so I know it says the size of the molecule, but you can think about it as relating to the molar mass. The greater the molar mass, the greater the London dispersion forces. The reason for this is that the greater the molar mass, that means it's actually a larger element, right? And all of these dispersion forces have to do with electrons, okay? So the bigger the element, the more electrons it has. And the more electrons it has, the more electrons it's able to shift left and right, like in these pictures. So more electrons means more electrons shifting left and right, which are going to cause greater London dispersion forces, okay? So more electrons equals more London dispersion forces, okay? I know I'm going to relate it to molar mass. Like when we think about it, I want you to think, oh, that one has a greater molar mass. Therefore, it has a greater London dispersion force. But that's not actually the reason, right? It has a greater molar mass, therefore, it has more electrons. And more electrons lead to a greater London dispersion force. Okay, so make sure to connect it back to the electrons. If you're looking for kind of a word to go with this, our word is polarizability. Okay, so The more electrons an atom or molecule has, the more electrons it's able to shift left and right, which means we say it is more polarizable because it's going to have a greater ability to be polarized. It'll make one side more partial negative and one side more partial positive because it has more electrons. So if I talk about the polarizability, I'm talking about the fact that it has more electrons, that it can shift left and right to give greater London dispersion forces. Okay, so we also see these London dispersion forces increase in hydrocarbons. Remember, carbon and hydrogen form non-polar bonds. So anything that is made up of all carbon and hydrogen means that that molecule is completely non-polar. We don't have to draw it out. We just see, oh, it's all carbon and hydrogen. Therefore, there's no polar bonds, so the molecule is non-polar. So since it's non-polar, the only intermolecular force that it can have is London dispersion forces. So we see as our molar mass increases, we're going to increase the boiling point. Okay? Remember earlier I was talking about the fact that an increase in the boiling point and an increase in the melting point is because of stronger intermolecular forces. We were talking about the fact that water had a higher melting and boiling point because it has stronger intermolecular forces. Okay? So those really strong intermolecular forces means that it takes more energy to melt it and more energy to boil it because it has to break the intermolecular forces. Okay, so same thing here. As we increase the molar mass, that means we are going to have more electrons. And if we have more electrons, that means it's going to be more polarizable, right? And it's going to have greater London dispersion forces. So if it has greater London dispersion forces, that means it is going to have a greater boiling point. All right, so thinking about all of that, which of the following molecules would have the largest London dispersion forces? Okay, go ahead and pause here. Come back when you're ready to see the answer. Alrighty, so looking at this, all of these just have carbon and hydrogen, which means these are going to have completely non-polar bonds. Therefore, these are all non-polar molecules. Okay, so since they're non-polar molecules, the only intermolecular forces they can have are London dispersion forces. And the strength of our London dispersion forces is going to completely correlate to our molar mass. So essentially, the one with the greatest molar mass is going to have the greatest London dispersion forces because it will have the most electrons. So here, the one with the greatest molar mass is going to be this one. Okay, the largest hydrocarbon, right, C15H32, will have the greatest molar mass, therefore it will have the most electrons, and therefore will have the strongest London dispersion forces. So here's our summary. Remember, the strongest bonds are going to be the intramolecular forces. These are going to be the bonding forces, and those are up at the top. So ionic bonds and covalent bonds. Those are our strongest types of forces, but those were not the focus of today's lecture. Out of the lecture today are intermolecular forces. The strongest one is a hydrogen bond. And remember, hydrogen bonds are not a bond. They are a very, very, very strong attraction. And remember, hydrogen bonds just want to have fun. So our hydrogen has to be bonded to a very electronegative atom in order to create that really big dipole here to make this interaction really strong. Okay? Dipole-dipole attractions are going to happen between any polar molecules. Okay, remember, hydrogen bond was kind of a special type of dipole-dipole interaction that was really strong. But dipole-dipole interactions will happen between any polar molecules. And we're going to see the partial negative of one line up with the partial positive of the other. Okay, and then our last one is going to be dispersion forces. And remember, these are going to happen in non-polar molecules. Okay, so our non-polar molecules are going to have a temporary dipole that happens because the electrons are going to hang out a little bit more on one side of the molecule or atom than the other. That'll make a temporary dipole which will induce a dipole in another molecule and create this kind of weak attraction that's happening here. All right, I want you to try this out. So this says indicate which major type of molecular attraction, dipole-dipole attractions, hydrogen bonds, or dispersion forces are expected between each of the following. Okay, so go ahead, pause here, and try this out. Come back when you're ready to see the answer. Alrighty, let's go over this. So if we look at NF3, NF3 will look like this. Okay, and the reason that I'm drawing this out is because by drawing it out, I can determine whether something is polar or nonpolar. This is going to be really important because that will tell us whether dipole-dipole interactions are possible, or can it hydrogen bond, or is it only going to have London dispersion forces. Okay, so here, when we have nitrogen and fluorine like that, we can see that this molecule is going to be polar. Okay, remember, fluorine is the most electronegative atom, and so it's going to make these bonds a little bit polar. So we see these dipoles that we can draw here. Okay, two of these dipoles will cancel out, but do you see that one can't cancel? So that means that this molecule is polar. And since it's polar, right, polar molecules can either have hydrogen bonding or dipole-dipole interactions. There's no hydrogen in this molecule, so that's going to be dipole-dipole interactions. Okay, let's look at chlorine, Cl2. So Cl2 will look like this. All diatomic molecules are always going to be nonpolar because one chlorine isn't more electronegative than the other one, so we can't put like a partial positive or partial negative on either one of the chlorines, so this is just going to have London dispersion forces. And then lastly, we'll have HF. Okay, so HF will look like this, and that is going to be a polar bond. Okay, so we'll put a partial positive on hydrogen and a partial negative on fluorine, and you'll see that we can make a dipole that doesn't cancel. Okay, so we know that this molecule is polar, and we can see that hydrogen is attached to one of those very electronegative atoms. So since hydrogen is attached to one of the very electronegative atoms, and this molecule is polar, therefore it can form hydrogen bonds. Okay. I do want to mention, because I didn't previously, that actually all molecules can have London dispersion forces, not just nonpolar molecules. The reason I really only talk about it with respect to nonpolar molecules is because in polar molecules, those dipole-dipole attractions or the hydrogen bonds are so much stronger that we don't really notice the impact of the London dispersion forces. We're only going to really pay attention to them in nonpolar molecules because there's no other attractions going on. But London dispersion forces are present in all molecules. They're just only important, really, in nonpolar molecules. All right, I want you to go ahead and practice problems 9 through 11 on the Chapter 6 lecture worksheet. And this actually concludes our lecture today. Today we learned about intermolecular forces, and so those are those forces that happen between atoms or molecules. Previously, we had learned about intramolecular forces, which are our bonding forces, but intermolecular forces, the ones we were talking about today, are the ones that impact the physical properties of a substance. They are going to help us better understand some of our physical properties that we'll get into in the next chapter. But today we talked about how they impact the melting point and the boiling point. Remember, the stronger the intermolecular forces, the harder it is going to make something melt or to make something boil, because those intermolecular forces are kind of locking those atoms and molecules into place and making it difficult for them to undergo a phase change because they're so strongly attracted to the other atoms and molecules in the substance. Okay, so make sure you get a lot of practice on recognizing which type of intermolecular force is happening. Again, the best way to do that is to draw out the Lewis structure and then to figure out whether your substance is polar or nonpolar. Remember, nonpolar substances will only have London dispersion forces, whereas polar substances will have dipole-dipole interactions and sometimes hydrogen bonding interactions. And they also have London dispersion forces, but like I was just saying, London dispersion forces aren't very important in polar molecules, so we usually don't talk about them. But the only way to be able to determine these intermolecular forces is to be able to draw the Lewis structure and then determine whether something is polar or nonpolar. So make sure you're getting a lot of practice on that. It's very important to be able to determine these intermolecular forces because we are going to use them moving forward. So make sure to get a lot of practice, and as always, if you have any questions about it, please let me know, and I'm more than happy to help you out. I like talking about these subjects because they're really interesting, and they're actually going to relate to our daily lives, which you'll see coming up. So if you have any questions, send them my way. Otherwise, I'll talk to you guys next time.